So we've covered the theory behind vector and parametric equations of planes. What I'm going to do here is I'm going to show you a couple of examples of them. What I want you to do is read the examples, pause the video, have a crack at them, and then come back and check your answers with the working I'm going to present here for you. Here you go. So I've simply got two questions for you. First one, I want you to find the equation of the plane through these points, but I want you to find it in all three formats we've covered. And then I want you to answer the question of what conditions must be met such that that point P lies on the plane with the given equation below. So pause the video and have a crack at those questions. So the first one, find the equation of the plane through the points A, B and C expressed in all three formats. So the first format, the Cartesian form, that's what we're going to look at first. So for this one, again, imagine we've got our plane here. There's my point A, B and C. What I'm going to do is find the vectors A to B and B to C, get my normal to the plane and my point, and then use that to define it in the format that we want. So let's do the vectors A to B. So A to B is going to be given by 2, 0, 2. So position vector of B minus the position vector of A. So 1, 1, negative 1. So that's then going to give me 1, negative 1, 3. And my position vector A to C, similar format, except it's the position vector is C this time, take away A. So 0, negative 2, 1, take away 1, 1, negative 1. That's going to give me negative 1, negative 3, 2. So what I now want to do is do AB cross AC to get my normal vector to the plane. So let's do that as we normally would. So there's my I, my J and my K, plus, minus, plus as we normally do. So AB is 1, negative 1, 3, negative 1, negative 3, 2, and then we just go through each component on its own. So we've got negative 1, 3, negative 3, 2 in the I, then got minus 1, 3, negative 1, 2, this in the J, and then plus 1, negative 1, negative 1, 3 in my K. So do each of these on its own. So I've got negative 2 minus minus 9, so negative 2 plus 9, so that's going to give me 7i. I've then got 2 minus minus 3, so 2 minus minus 3 is 2 plus 3, which is 5. So it's then going to be minus 5j. I've then got 3 minus 1, so that's then going to give me plus 2k. Now remember, Cartesian format of the equation is A dot R equals A dot P. Now A, remember, position vector of a normal. P, position vector of the point on the plane. So in this case, my P is going to be the position vector of A, which is going to be given by 1, 1, negative 1. And the R we take to be our generic point. So the R in this case is given as the X, the Y, and the Z. So let's plug all of that together. So what I've got now is 7, negative 5, 2. Scalar product with my X, my Y, and my Z equals the normal. So 7, negative 5, 2. Scalar product with my P, which is A, 1, 1, negative 1. So from that I can write it out that 7x minus 5y plus 2z on the left is equal to, well, I've got 7 minus 5 minus 2, which is 0. So there you go. That's the Cartesian form of the equation of the plane containing those 3 points. Now, if we look at the vector one, what we have to remember is for the vector, it's R equals A plus TB plus UC. So what I'm going to do for this one is the A is the point through which they are. So A is going to be given by this A here, the 1, 1, negative 1. The B, that's going to be set equal to the AB, and the C is going to be set equal to that. So what that means is I can say find R is equal to A, so 1, 1, negative 1, plus T times the B, so plus T times 1, negative 1, 3, and then plus U times the C, negative 1, negative 3, 2. I can then just take that and modify it for the parametric one. And what I can write is that R, combine each component, is 1 plus T minus U, 1 minus T minus 3U, and then minus 1 plus 3T plus 2U. Right, each component out on its own. I've got XR equals 1 plus T minus U, YR is equal to 1 minus T minus 3U, and ZR is equal to minus 4 plus 3T plus 2U. So there you go, parametric version there. And obviously, dependent upon the values of T and U that I choose, I'd be able to find any point upon the plane that I'm after. So there you go, that's all three of them, all three different formats that we need and that are used there. Second question is, what condition must be met such that the point P is negative 8, 9, 14 lies on the plane with the equation 1 minus 3t plus 3u plus 2 plus t plus 3uj plus negative 1 plus 3t plus 3uk. So what condition must be met there? So what we know is that if we were to separate this out and look at xr, yr, zr, that there would be my xr, that there would be my yr, and that there would be my zr. Now if I wanted to find this point here, what I know is that 1 minus 3t plus 3u is equal to negative 8, 2 plus t plus 3u is equal to 9, or negative 1 plus 3t plus 3u is equal to 14. Now I have to find the t and the u for it. If I find t and u which satisfies this, what I'll then have is my point P. Now t and u are two variables, so I need at least two equations in order to be able to solve them and get it. Now, there's a couple of ways I can do it. First way is I can approach it by putting them all in a matrix. Second way, which is actually much more straightforward, is I can use simultaneous equations that we've covered previously by picking any two equations. What I can then do is use the third equation to check my solution. So what we'll do, let's imagine we'll pick these top two equations here and rearrange it so I've got t and u on the left hand side. If I was to do that, I'd have minus 3t plus 3u equals negative 9. I'd then have t plus 3u equals 7. What I can do is, because my u's are with the same coefficient, if I subtract them going down the way, what I'd end up with is negative 4t equals negative 9 minus 7 is equal to minus 16. So I then end up with the fact that t is equal to 4. If I then go back and substitute t is equal to 4 into either of these two equations, so let's say this one, I'd have 4 plus 3u equals 7. So 3u is equal to 3, so u equals 1. What that means is that's the values of t and u, which would satisfy these two at least. Now I can use a third one to check, because if I put t equals 4 and u equals 1 in here, what I should end up with is this left hand side equal to the right hand side. If that's the case, I've got the right values. So what I could then say is fine, so I've got minus 1 plus 3t, so plus 3 times 4, plus 3u, so plus 3 times 1. What that means is that's equal to negative 1 plus 12 plus 3, which equals 14. So I've got exactly what I want. So what that means is therefore for P, that occurs when t equals 4 and u equals 1. So that's the parameters I need in order to get that point on that given plane. So we could approach it either of the two ways I just mentioned at the start. We could have used a matrix if we want. I find this way a lot more straightforward purely because we're only looking for 2 unknowns. If we were looking for 3 unknowns, so we had a scenario where we had that, then possibly matrices would be a bit better. But I prefer this. It's much more straightforward and a good hark back actually to National 5 mathematics. Brings all that back into play. Who'd have thought Nat 5 at advanced higher level, eh? Great work. So that there is what would occur then. Now, just a point to note, I could have picked any of these 2 equations to solve. If I'd picked any of them, I should still have ended up with the t equals 4 nu equals 1, and I could have still used the last equation I hadn't touched just to verify my solution. Wouldn't matter which I picked, I should still get the same answer.